The topic of our mini project is a unified invariant learning framework for graph classification. Uh, I myself, Swaksh Patwari, Anuj, Lalla, Rajan, and Ansh Dubry have worked on this topic. So the problem is of out of distribution learning. In machine learning, training and test data are commonly assumed to be IID, but in out of distribution setup, IID assumptions does not hold. That means that the training and test distributions are not same. So in the common out of distribution settings, there is concept shift and another is covariate shift. So in this figure, we can see that these two types of, there are two types of way to split data for training in auto distribution settings. In the first one, there were five domains are denoted as different colors, where each domain include output of the same distribution. We sort the data set according to the domain DI, then group them into train, validation, and test sets. And in the another illustration of concept shift split, each concept includes all three domains, but each domain has spurious correlations with a specific output in a concept. For example, in concept C1, the domain colored in red is highly associated with Y1, but this domain corresponds to Y2 in concept C4. Also note that the distributions of concepts in training are similar. For a covariate shift, the training and test examples are from different domains. And for a concept shift, examples are chosen from same domain with different labels to show the different domain output correlations. In also how the graph in out of domain distribution typically different from general OOD. So due to the non-Euclidean nature of graph data, directly transferring the penalty term from out of distribution algorithm to graph learning poses a challenge, and it often leads to a suboptimal performance. In this taxonomy of typical graph out of distribution solutions, there were three methods of generalization, which includes data, model, and learning strategy. Our paper is contains graph invariant learning. So, in the invariant learning, this paper proposes a solution which falls in the invariant learning paradigm. This typical approach in invariant learning, we can see from the figure. This architecture mainly comprises of three components: the feature extractor network, the GNN encoder, and the classifier. The core idea is to extract stable features via the feature extractor, subsequently inputting these features into the GNN encoder and classifier for predictions. If the feature extractor can effectively capture stable features in graph data across all possible environments, then the model can achieve excellent generalization under distribution shift.
Anuj this side, and I will be talking about the algorithm implemented in the paper. So essentially, the core idea is to extract stable features from the feature extractor. So stable features means those features that can achieve excellent generalization under the distribution shift. So author claims that existing methods they fail to extract what they term as minimal stable features. As an example, what these features are is, let's take a molecular graphs. In molecular graphs, COH group determines acidity while NH2 influences reducibility. So these are examples of minimal stable features. Like for every molecule containing COH is the stable feature. We can say that it is acidic owing to COH. And typical methods they extract stable features which consist of minimal stable features and stable environmental features. Stable environmental features are noisy features. They are not really stable features, but they emerge in training data. As an example, let's say my training data coincidentally has all aromatic compounds with COH. So the model accidentally makes a spurious correlation that if you have an aromatic ring, it is acidic. Now, let's say in test data, there is an aromatic ring with NH2. It may not be acidic, but still it has learned the correlation that it is acidic. So that is a noisy feature known as stable environment features. So we don't want such features. This is the overview of the entire UIL method. Feature extractor extracts the stable and environmental features, followed by a GNN encoder, which is a graph level GNN encoder, which is followed by a classifier. And this is for the semantic invariance. In structural invariance, we learn something known as graphons, and we try to make the representations of the graphons per class per environment close. So it is explained later in the loss function. So how we do the semantic invariance is, the model is a composition of the feature extractor, GNN encoder, graph level, and a classifier. So we need a mask for the stable features. So the Z here is obtained by a GNN encoder, which is different from this one. This is a node level GNN encoder. It extracts the node embeddings, passes it through an MLP followed by a nonlinear activation, which gives us the mask for the node level mask. Similarly, for pairs of node embeddings, we extract S level mask. One minus this matrix would be the mask for the environmental features. This was for the stable features, it would be for the environmental features. To extract those features from the graph, we simply perform a Hadamard product with the adjacency matrix. The idea behind structural invariance is Graphon, it is a function which simply takes latent coordinates of nodes and gives the probability of an edge existing between them. Very simply, Graphon can be understood as a structural representative. Like they say stable Graphon. So we fix the label Y. We For a particular environment, we take all the graphs with the label Y. We extract their stable features, and from that we come to a stable graphon. So it can be understood as a representative for that particular environment, for that particular label. So essentially, we extract multiple such representations for a fixed label across environment. So for each label, each environment, there would be representation called stable graphon, and we bring them closer. So the structural invariance objective is to take these graphons from different environments, and suppose label is fixed, so just this term holds, and we bring the graphons across environments closer. This is the Frobenius norm, and then we iterate it across the classes. For the sufficiency objectives, one of the objectives is that we just consider the stable features, and using just the stable features, we need to predict the label correctly, which is what the stable features were actually, causally determining the label irrespective of the other features. This is simply a regularization loss so that the masks extracted are not trivial. So the sufficiency loss is a combination of these losses. And in the semantic invariance objective, we fix the stable features obtained from a graph. And for that particular label graph, we take the environmental features for the same label across environments, like this image can be seen. A fixed stable feature extracted, summation taken across multiple environmental features. It is a sort of a counterfactual, and then we pass that representation through our classifier to predict the label, and this forms the semantic invariance objective. And our final objective is a combination of these alpha and beta hyperparameters. These are the results. It can be seen that UIL, it performs better on average than all the existing algorithms. Ansh will take it from here.
So now let's look at our experiments. The motivation was that our reported OOD baselines were outdated. So we retested with stronger algorithms and made graphon estimations learnable. The screen algorithms were ERM++, URM, and RDM, which are state-of-the-art models algorithms. The graphon learners are 1. MLP-based, 2. Low-rank factorization, where U of y belongs to R of n cross R, and WY, which is our graphon, is a softmax on UY into UY transpose. The findings were that only ERM++ and the rank approximation were promising, so we scaled them to more datasets. The ERM++ recipe was just label smoothing plus software plus stochastic weight averaging, which is SWA. Now let's look at some datasets that we experimented on. The good HIV dataset is composed of molecular graphs. We perform binary classification on them, which is HIV replication is possible or not, evaluated under covariate scaffold size, and the concept shifts. The metric was ROC, area under the curve. Next is the good CMNIST and good motive, which were both multi-class classification and thus judged on accuracy. ERM++ was uh, ERM++ was stronger on default with label smoothing plus SWA, no invariance loss. ERM++ is competitive or best in two-thirds of the task under our feed fixed seed, which is the default hyperparameter protocol. The per task winners were good HIV, scaffold ROC, ERM++ was 61.52, and good CMNIST, the ERM++ was 31.61, while in good motive, UIL performed best with 61.67. The What we could see basically is that UIL rank is almost equal to UIL itself. That means low rank learned graphon performs close to the reproduced UIL, and the gains are modest without heavy tuning and track of graphon schedule or weight. Next, let's see why hyperparameter sensitivity plus limited tuning was possible in our case. So we had to tune many knobs, which is alpha, beta, rho, and there were a lot of variable environments, LR, a learning rate, and batch, which weren't fully swept with defaults. And the structural semantic effects were intentionally small in our case. The graphon updates were late and sparse. The graphon loss runs only at epochs 80, 90, and 100, and thus with this low weight, it rarely shifts the solution. Last is our strict best validation selection. We pick the single highest value epoch and the later epochs with equal rounded validations, but better tests aren't chosen, which avoids leakage but can hide late gains. The compute load, even with low rank graphons, with each gate step still touches n cross n matrices per class environment. The time spikes at epochs 80, 90, and 100 and was largest on HIV. The memory took O of n times R with the temporary compute of O of n square, which was fine for CMNIST but not trivial for molecules. The tuning is the bottleneck. Best UIL results hinge on some alpha, which is structural, and beta, which is semantic, and other variables. And full sweeps are very costly. Under realistic budgets, that is no massive sweeps, ERM++ is a strong, simple baseline which won on HIV and CMNIST and close on motive. UIL learned rank is almost equal to reproduced UIL. Bigger gains needed earlier or more frequent graphon updates, and non-zero semantic weight means more tuning plus compute. This is all from our side. Thank you so much.